Good evening, welcome to tonight's talk on CHP, Combined Heat and Power. Before we go any further, the usual housekeeping. We've just reminded there a while ago, telephones powered off or silenced, please. Escape routes, the way you came in or the door behind you. If you haven't signed in to tonight's event, would you please do so that Clyde Road, the headquarters, get some measure of the activity that's going on in the region, and we get a bit of credit for organising events as well. You know, it does help. Those of you out on the web, do as you please. It doesn't really matter to us, you know, but you're welcome anyway. Before we go on to tonight's event, next week there's a lecture on wind farm engineering and the challenges of marrying concrete with peat. There's the following week there's a lecture on modular and panelized construction of houses. During the month of February, every Monday, there's a lecture on different aspects of facilities management. Those talks are not up online yet, but they will be advertised shortly. Our friends in the southeast region have advised us that there is a site visit at Bosch and Long on February 7th, so if anybody's interested, you can get onto the southeast region for that. And given that Mr. Lapthorn is in the room, it would be remiss of me not to mention the annual Cork Region Dinner, which is on February 8th on the other hotel in the Douglas area, and is generally a good night had by all, and we'd love to see you there. So tonight's speaker is Kevin Fortune. I've known Kevin for about 5 years, I think it was, since we met at a chartered interview. Kevin is originally a mechanical engineer. He's a chartered mechanical engineer. He's with Fingleton White for about 10 years. He's been teasing me on some of the work that they've been doing on combined heat and power and what can be done in the domestic space amongst other spaces. So I'm really looking forward to finding out what's behind those theses. So Kevin, please.
Thanks, Paul. So energy efficiency is what it's all about. It concerns us all. Governments, industries, engineers. Some of us work in the energy field, some of us don't, but we all pay gas bills and electricity bills at home. So we're always trying to find ways to reduce our energy consumption. There's two reasons for that. One is the climate change challenge, which is we hear about every day in the news. You have need to reduce your greenhouse gas emissions, and the other is money. We don't want to be spending money on energy bills that we could be spending on whatever else we want to spend it on. So I'm delighted to come here this evening and talk to you about CHP as a means to save energy. And I'm a mechanical engineer based in Little Island. I work on gas CHP, biomass CHP, solar PV, energy efficiency at industrial scale and utility scale. And I've been working on developing a domestic CHP product for a good number of years now, but we're approaching domestic trials. So plan to start domestic trials in an actual house this year and move on to a pilot run next year, 20 units. So a quick introduction to Fingleton White. We're a multidisciplinary engineering consultancy, 70 engineers between Portlaoise, Dublin and Cork. Fields we work in are energy efficiency, infrastructure, gas, water and oil infrastructure projects, boiler houses, solar PV, wind and biomass projects. And we also develop industrial gas turbine CHPs on a design, build, own, operate model. So, what I'm going to talk about tonight, well actually you've told us what CHP stands for. It's combined heat and power. Everyone knows that at this stage. The first thing I want to do is give you what the definition of what is combined heat and power. What you're looking at here is a waste heat recovery boiler, and then far in that photograph there's a gas turbine. Combined heat and power is the generation of useful heat and electricity in a single process, which leads to very high efficiency. I want to really emphasize tonight that it's a heat-led process. The starting point for any CHP project is the heat. If you don't have a heat load, you don't have CHP. The thing is that electricity, obviously, you all know, can be exported to the grid, and it's very easy to generate electricity in Clare and supply it to Dublin. Heat, you can't transport it like that. So it's very important, and it's the number one mistake that people make when they're considering CHP, is they think about the value in electricity and they don't think about the heat. So I'm going to be going on about a good bit about that tonight, so you'll definitely take that home with you. The types of projects that we're normally involved in are like 12-13 tons an hour of steam, and the domestic CHP project is 5.5 kilowatts of heat. So there's a 2 kilowatt generator associated with that. So that's a big difference in heat loads, but the benefits are the same. And to talk about the process, this shows the kind of very typical gas-fired CHP unit. What we're looking at here is the fuel coming in on the left-hand side into either a reciprocating engine or a gas turbine. You have that's driving the generator and generating electricity, which is either used on site or exported to the grid. And then you have heat recovered from the gas turbine, raises steam to provide heating to the local facility, wherever your steam or hot water. Like, as an example, there is a CHP in this hotel here that's probably powering this projector that we're looking at, and the heat is driven by an internal combustion engine, and the heat is recovered to heat the swimming pool in the building. So it's used in a lot of places that people mightn't be aware of. So by implementing CHP here in the hotel is making the best use of the gas that they're burning. And what do I mean by that? Well, if you generate that heat and electricity from two separate processes, you end up burning more fuel, so that ends up costing more, and it ends up emitting more emissions. So that's what it's all about. There is another type of CHP, biomass CHP, which I have done some work on, and really what we're talking about here is the difference is that the fuel is burnt in a biomass boiler to raise steam, and you have a steam turbine then. And depending on the heat load, you select your steam turbine. The steam that you get or that you need to supply your heat load is taken off typically at whatever stage of the turbine that you need it for, or you have another iteration of that is if you have a very constant heat load, you can use a back pressure steam turbine where all the steam goes through the full length of the turbine before going into the heat load. It's exactly the same thing, but by far the most common CHP, let's say 98% of the CHPs in Ireland are gas-fired CHPs. What you have then, to give a little bit of context on this, CHP in Ireland, what we're looking at here is where we rank in the EU 28 in 2016. You can see the uptake of CHP in Ireland is very low, and there is potential there to increase that uptake. What does that mean in real figures? You know, we're talking about 7.3% of our electricity in this country is generated by CHP, and that's 1,887 gigawatt hours of energy that we save by using that technology. That's what the energy savings are. That's about 423,000 tons of CO2 saved or emitted, avoided. We didn't emit it. If we had supplied those heat loads by two separate processes, we would have emitted an additional 423,000 tons of CO2. So it's a big reduction, but there's a lot of potential to do more. to put it into context, further context, the emissions from the whole country in a year, it's 60 million tonnes is what we emit. So 423,000 tonnes is small relative to that, but it's not insignificant. So the main reasons you'll invest in CHP is really its energy savings, and those energy savings lead to reduced costs and reduced greenhouse gas emissions. And where do those energy savings come from? Well, there's an equation which I'm going to go through, which you use for calculating the energy savings, and it comes from the EU Energy Efficiency Directive. What you do is you compare the production of heat and electricity in separate processes, and with those separate processes, you make a small adjustment for transmission losses. But anyway, I'll get to that. Before I go on to that, I'll just go through the calculation itself. I'll just give you a block diagram as to where the savings are coming from. So if you look at this, what we're comparing here is the conventional system on the left-hand side and CHP on the right-hand side. And both systems are outputting 30 units of electricity and 50 units of heat. What you have is 100 input on the CHP side of fuel input, and typical efficiency of industrial CHP would be 80% or higher. So you have losses of 20, and that gives you overall efficiency 80%. And on the left-hand side, then the electricity production is at 42% efficient. So you need to put in 71 units of energy to get that 30 units of electricity out of it. And then the heat production at 81% efficient, you put in 62 units of fuel and get 50 out. And then if you see down the bottom, you have the inputs 133 and inputs of 100. And that difference is where the energy savings are. And they are real, and the CRU regulates this. Every year you make a submission to the CRU based on your production figures, and that's what it is. So now we get into the equation. It's not a particularly heavy equation, so PES stands for primary energy savings, and that's what it's all about. That's what's at the core of CHP as a process. And how you calculate the primary energy savings? Well, you've got the CHP heating efficiency, which is the heat output from the CHP divided by the fuel input, and that's useful heat output. I have to introduce the concept of useful heat because it's very important. Useful heat is a heat load that would be met by it's defined in the directive as an economically justified heat load. So one that you would have provided heat for without the CHP. And then the CHP electrical efficiency is fairly obvious. You take the electrical output from the generator and divide it by the fuel input. The two reference values then come from a separate regulation, which is published by the EU. To qualify as high efficiency CHP, you need to achieve 10% or more for systems that have an electrical capacity greater than 1 megawatt. And for systems less than 1 megawatt, it's primary energy savings greater than 0%. So if you're less than 1 megawatt, it's not an overly arduous goal, but for greater than 1 megawatt, it's 10%, which is also not too difficult to achieve, as you'll see in the results from the worked example. So the CRU provide us with these, this spreadsheet here, which I've placed into this presentation. And from the top here down to here is the figures that you need to fill in dependent on your CHP. So you select the type of CHP it is. This is a real work example from last year. Gas turbine with heat recovery. The fuel is natural gas, and the electrical capacity of that plant is 5 megawatts. thermal rating 8 megawatts. The year construction is important for the reference value, so that's why they're asking for it. And it's the same with the voltage. The grid connection voltage, depending on what you're connected at, they've got different correction factors for the electrical efficiency, the reference electrical efficiency. So, and then depending on whether you're importing, or sorry, you're exporting or using it on site, there's a separate correction factor for that as well. So that's the CHP. Then you have your production stats here, the electricity output, and the useful heat output, and the fuel input. And then the spreadsheet turns these values and does a check. So if your overall efficiency is above the threshold, which is 75%, then all of the electricity generated in a gas turbine CHP qualifies as electricity from high efficiency CHP. There is most of the types of CHPs that you'd be coming across have that threshold at 75%, but there are two that have a higher threshold of 80%, and that is combined cycle gas turbine CHP and condensing steam turbine with extraction. So if you've got either of those two, there's a higher bar for those technologies. And then the spreadsheet tells you, yes, you've achieved this threshold. The next section then, we have two blank sections up the top here, because if you fall below that threshold, it doesn't necessarily mean that all of your electricity is not high efficiency CHP. There's a heat to power ratio for your plant, and that heat to power ratio determines how much, based on your useful heat output, a certain percentage of that electricity can still qualify. But you do need to achieve the primary energy savings. So that, in this case, that figure is exactly the same as what was on the previous page, but it would break out non-CHP fuel if you were below the threshold. Now you're taking your electrical efficiency and your heating efficiency as calculated on the previous page. The reference electrical efficiency and heating efficiency are the next 2 points there, and the reference heating efficiency, nothing happens to that, but the reference electrical efficiency is adjusted for to account for the transmission and distribution losses that you would have incurred on an electrical system. So obviously, if you use it on site, those losses would be higher, but if you're exporting it, you incur some of those losses. So that's what's happening here with these two different figures. The climate adjustment, the reference value for electricity generation is based on standard temperature of 15 degrees. For every degree you go below that, you add on 0.1% of an efficiency to correct for that, because in colder climates you get better efficiency from the plant. So that gives you your reference value here. And then you get primary energy savings of 19.8%, and you're over the 10% threshold, so that works very well. But really, what does that mean to everyone here tonight? Because you probably won't really appreciate it until you see this. And what we're looking at there is, from this one plant, there was 31,702 megawatt hours saved. And really, if you think about your house, 4.5 megawatt hours is the annual consumption for a house. So about 7,000 houses would be powered by those energy savings. And there's the CO2 that was avoided, 6,374. One plant, 1 year, every year. So I think that's good. So here's the 8 CHP plants that we operate, and there's a variation in these are the registered or the figures as per the CRU process. So there's a range of primary energy savings, which is down to the kind of the electrical efficiency, the site load, and the way the site operates based on heat load, really. These 8 plants combined had energy savings of 295,000 megawatt hours, and that's a lot more houses. 60,000 tons of of CO2 avoided. So the benefits, apart from significant energy savings and avoided CO2 emissions, what you're looking at with standard industrial CHP is 10 to 15%, and it is the same for domestic, which we come into very shortly, but 10 to 15% on your electricity bill, a simple payback of 6 years, CHP efficiency greater than 80%, and CHP availability greater than 96%. You also have island mode operation where you can keep the site up in a blackout situation, and you have increased steam reliability through having an extra boiler on site in the CHP. There is a carbon tax rebate for high efficiency CHP, which is another benefit. If you're thinking about improved security of supply, apart from the island mode where you have keep the site up during a blackout, you also have reduced imported fossil fuels into the country, so there's increased security of supply for the country as well. And the other thing is the transmission and distribution losses in Ireland. It's about 8%, which is avoided by generating the electricity at the point of use on the site. So well, now we'll move on to the domestic CHP. So yeah, here we go, domestic CHP. Domestic CHP is the same process that I've just gone through that is tried and tested in industrial processes. And in a house, what you have is electrical loads getting switched on and off continuously. You have kettles getting switched on, lights getting switched on. The load is not very continuous, but the heat load is reasonably continuous. And what we're looking at here is you're burning gas in an engine, an internal combustion engine. You're recovering heat from that engine to supply hot water to the cylinder and to the radiators in the house. And then the electricity generated is either used on site or in the house or exported. And that's domestic CHP. The benefits are identical to the industrial benefits that I just went through there. But there is one additional benefit with domestic CHP, and it's to do with the winter peak. So people who are familiar with the winter peak, between 5 and 7 every evening in winter time, electricity demand spikes in the country. And what we're looking at here is the profile from a couple of weeks ago in Ireland, where this is nighttime operation here, and this is daytime operation, and then between 5 and 7 we get this very high peak, and that's when all the inefficient, or not inefficient, but the less efficient generators are brought on to meet that load. So in order to, if we think about when you switch on your heating in the evening, it's at this time, and if you have 100,000 units of these installed in the country, that would generate 200 megawatts of electricity, and it will be 200 megawatts that would come off this peak here. And on my next slide, I'll just zoom in on a particular day. And what you're looking at here is the blue line is the profile which I showed you on the previous slide, and the red line is the profile as it would be if there was 100,000 domestic CHPs installed in Ireland. And you can see in the morning it's switched on for a couple of hours, and in the evening it's switched on for maybe 3 or 4 hours. And it's basically delaying the ramp up in the morning and shading the peak in the evening. And you're shading the peak with efficiencies of 90%. That's what it is. So here's a picture of our prototype in the lab. We have a lab set up in our Dublin office in the ground floor there. And that's what it looks like. Generally speaking, domestic CHP hasn't really taken off yet. The main reasons is because developers haven't overcome the problems that are inherent when you're trying to put an internal combustion engine into a house. You've got noise issues, vibration issues, You need to have a high electrical efficiency to make it pay. You also have, well, the main reason is cost, because there are systems available in the market, and there has been support mechanisms put in place for those systems in the UK. Fairly good supports, but the systems haven't sold. Like all CHP projects, the outlay up front to buy this system needs to be paid back within 6 years or less, and just the costs are too high at the moment. So, just to talk specifically about a couple of issues that we faced in developing the product, we have noise and maintenance interval has been two particular issues. If you think about anyone who's got a petrol lawnmower, think about 90 decibels and try putting that into a house. Not going to be too much sleep in that house in the mornings, and not going to be too comfortable either. We have overcome that problem, and the way we did it, on the left-hand side here, you can see the acoustic panel that is being taken off the side of our machine there. We have a polyester sandwich here with a vinyl backing that's attached to the steel panel, and that's what makes up the acoustic enclosure. And then we have vibration mounts on the machine itself and on the engine mounts. So that combination actually brings down the noise substantially. There's a company called Ventac in Blessington, an Irish company that supply the acoustic material and the vibration mounts, and it's been very successful. The other issue, if you think about a domestic situation, you can't come into service this thing any more than once a year because it's too disruptive for the householder. So this machine will run 2,000 hours a year, and in order to run 2,000 hours a year, if you take that and put it onto miles in the car, or kilometres, we don't have kilometres these days, that's 120,000 kilometres. So it's a big service interval, but the loading on the engine is not too high, and we operate at low RPM. There's two reasons to operate at low RPM. One is the noise issue, and the other is service interval, to lightly load the engine. Another thing is an extended oil sump, so you have a large capacity in your oil sump. That's really maintenance interval. So here are some test results from a typical day of our system in Dublin heating our office. And on the left-hand side of this chart, you can see the electrical output, gas, and heat output. So that's in kilowatts on the left-hand side. So this system outputs, it's designed around a 2 kilowatt generator and a 5.5 kilowatt heat load. And what you're looking at is a gas consumption of 8 kilowatts here, the green line, and that gives you an overall system efficiency of about 90%. So if we take that particular day, the electrical efficiency was 23%, 23.5%, the heating efficiency was 66%, and the average overall efficiency for the day was 89.4%. Putting those figures into the previous calculation, primary energy savings are 21.5%, and that's the equivalent of what we get in an industrial gas turbine CHP. It's substantial savings, and really the question is, why aren't we selling more of them, or any of them? But the reason is because, well, we need to verify those savings, because those are in a lab situation. We need to get it into a house and try it out for a year and see how it goes there, and verify that these savings can be achieved. So the other thing is cost. The prototype that we've built is quite expensive. So the next, there's the internals of it. We are planning to introduce this to the UK market. In Ireland, there's no support scheme for domestic CHP, but in the UK there is a support scheme. Has been one for since 2010, and there has been a very low uptake. But there's about 1.5 million gas boilers sold in the UK annually, and this kind of system would be more suited to larger houses. You'd be expecting, install rate of around 20,000 a year, which would lead to 600 megawatts of domestic CHP on the grid for very little investment in grid infrastructure. And the same problem which I outlined about the winter peak occurs in the UK as well. So it helps in that. Like sales in the UK are in the tens of units at the moment, and PV sales, since they introduced this feed-in tariff in the UK, PV sales have been 900,000. So there's been a big divergence. In PV has been very successful. Domestic CHP has not been, and they haven't gotten up to the volumes where the costs come down. The suppliers that are operating in that market. So it's kind of a chicken and egg situation with them. There isn't any real reason other than the cost of the systems that is preventing it from following the same growth path as PV. So, well, at present in Ireland we don't support domestic generation, and last year there was a PV grant introduced for solar panels that people put on the roofs of their houses. And while that's welcomed, it's not really a good approach, because the problem with a grant is it doesn't encourage efficient behaviour, and you need to encourage efficient behaviour. A feed-in tariff will be much better, because the issue with giving a grant is that it encourages people to switch on loads that they wouldn't have otherwise switched on when they're generating, rather than give the electricity out to the grid. And if you do that, you haven't saved anything, because all you've done is create an extra demand for electricity rather than offset electricity with renewable electricity. So we're very much in favour of a feed-in tariff or net metering, which is used in other jurisdictions for domestic generators, including PV and domestic CHP. Another sort of issue in Ireland, or not an issue, it's a positive, is the inform and fit process, whereby people can install generators in a domestic situation. It has to be a type approved grid connection by the ESB networks, but you just fill out the form, send it to them, and so it's a very easy process in comparison to the larger generators. And that's good. It just does need to be accompanied with a feed-in tariff. And the reason is to encourage better behaviour with electrical loads. Another very simple thing that could be done to encourage the uptake of the technology is to change the way the PSO is currently charged to individuals or to anybody. Like at the moment, it's charged on a KVA, so every house in the country pays the same PSO levy, regardless of how much electricity they consume. Well, that doesn't encourage any kind of change in behaviour. If people were paying on the kilowatt hour, that would encourage a change in behaviour, and it doesn't cost anything. You charge the same amount, you just distribute it slightly differently. And there's a lot to be said for making that change, but it hasn't happened yet, and maybe it will in the future. So that's sort of a high level view of what we have done with domestic CHP. The next thing that's good about CHP is how it interacts with renewables, because as more and more renewables come onto the grid, it's a challenge. They're intermittent. They don't operate all the time. So just a couple of examples of how CHP can interact with wind in a very positive way. What you have is, well, there's two examples. One is in the industrial situation. If you install a 5 megawatt gas turbine, there isn't any reason why that can't modulate to work with a wind turbine. So you've got a wind turbine and a CHP feeding into the same transformer, and what you've got is the wind turbine will use that about 30% of the capacity in the year. Is the production figures for the wind turbine. And the CHP covers the other 70%, and then like you're wondering, well, what happens to the heat load in that situation? It's common practice to use supplementary firing in a CHP, and that's where you burn gas in the duct between the gas turbine and the waste heat recovery boiler. And if you supplementary fire, you can continue to supply 100% of the heat from the CHP, although the electrical capacity can be dropped down to, you know, the minimum running frequency or power of the generator. And so that's one way CHP interacts with wind. And the other thing is, if we're talking about domestic CHP, I mean, it's a very responsive generator that could be brought on, you know, with the development of the Internet of Things and connectivity and smart grid. There's no reason why domestic generators couldn't be brought on to back up wind, and you know, 200 megawatts at peak times is not insubstantial. So that's how CHP can interact with wind in a positive way. The other renewable that is very prevalent, and it's something that's, well, there's a very good fit between domestic solar PV and domestic CHP, because domestic solar generates electricity in the middle of summer or in the daytime generally, and domestic CHP generates electricity in the morning, a couple of hours in the morning, cold dark mornings, and then in the evening, cold dark evenings. It's a wintertime operation, and they don't need separate grid assets. They connect through the same grid asset. They have very similar output. I mean, 2 kilowatts wouldn't be non-typical for a PV system installed on a house, somewhere between 1 and 2 kilowatts. And as we've seen the growth of PV in the last 8 years in the UK, where you have 900,000 of these systems installed, you have ideal candidates there for domestic CHP, mainly because the people who've installed them are obviously interested in reducing their carbon footprint, and they are willing to invest to take action to reduce carbon emissions. So I think it's a very interesting connection between the two. The final part of renewables and CHP is biofuels, and that's like biomass and renewable gas. In the case of renewable gas, which comes from anaerobic digestion, what has happened historically is the anaerobic digestion gas is generated on a farm or someplace remote to heat loads, and the gas is burnt in a CHP, but there isn't much of a heat load for a CHP, so it can be more of a generator than a CHP. And in order to overcome that problem, well, from a CHP developer's perspective, what is interesting is the injection of renewable gas into the grid, which Gas Networks Ireland have a project started, and they're planning to introduce 20% renewable gas into the gas grid. Now, the use of that gas, I mean, the best use of that gas from my perspective is in gas CHP, and you know that further improves the carbon reduction potential of that renewable gas. I mean, renewable gas has the potential to decarbonise home heating the same way biofuels have decarbonised the transport network without anybody really knowing about it. You know, through blending biofuels in diesel and petrol, we've seen a reduction in our carbon emissions associated with transport that most people are unaware of, and renewable gas can do the same thing for home heating. Domestic CHP is a step again in the right direction to maximise the potential of that renewable gas. The other thing to think about is biomass, because there is a limited supply in biomass in the country, and making best use of that would be to burn it in CHP. The CHPs where you burn biomass need to be located close to heat loads, and that is maximising the use of a limited resource. So, like CHP is a key enabler of biofuels to maximise their decarbonisation potential. So now, last slide is just to summarise what I've gone through this evening. What we're talking about is 22% primary energy savings. That's for the domestic CHP system. The other benefits I'll not read out to you, but what I have talked about is heat load. CHP without heat load is not CHP. There's a broad range of technologies to meet different heat loads from domestic situations. There are products available on the market already. This hotel here is another example to gas turbine industrial situation, and bigger again, very large gas turbines. It's about 160 megawatts, I think, of Linish. So the steps that are needed to encourage domestic CHP, we need either a feed-in tariff or net metering to encourage all domestic generators, not just domestic CHP, and a change to the way the PSO is charged is an important price signal to encourage energy efficiency. The next steps for us in this project is to move on with our domestic trial and get it into a house and verify that 22% energy savings can be achieved in a house, and then move on to a pilot run following that, 20 units to further verify them. Final statement today: CHP is a tried and tested technology which reduces greenhouse gas emissions and energy consumption. And with energy efficiency at the centre of EU policy, should be new targets that are coming out, 30% energy efficiency by 2030. CHP is going to play a major role in achieving that target and transitioning to a low carbon economy. And I think, well, I invite a lot of questions this evening on the subject if anyone wants to. That's it. Thanks.
Sorry folks, I might ask you just use the mic just so that people on mic can hear you. Any questions?
Hi Kevin, what are the savings or the carbon savings associated with micro CHP?
It's about a tonne a house. That's, somewhere between 900 kgs or a tonne a year would be the savings on a domestic CHP system.
I see on the graph that most of the CHP uptake in EU countries are all in colder countries, bar Malta, for some reason that was up there as well. Is the lack of uptake in CHP in Ireland related to ambient temperature? Is that because you were saying there's a 0.1 increase as the temperature goes down?
No, it's not. It's not down to that. The ambient temperature is only doing a correction for compared against the electrical efficiency of the grid. That's not the reason. I mean, a lot of the reason would be there are support schemes in other countries which we don't have here, or district heating might play into it. We don't have district heating systems here, but it wouldn't. I would say support schemes is a lot to do with it, and also like the likes of Denmark, where they have very high penetration of CHP, would be down to regulation, as in you have to build a CHP plant. So more support would see more CHP on the grid.
Thank you. Will the system run at maximum output in the domestic scale?
Yes.
All the time?
Yes. And that's why it needs an export tariff, because at 2 kilowatts you will be exporting a lot of your electricity. If you're not getting paid for that, you're burning gas, you're buying gas to generate that electricity. If you're not getting paid for it, it's pointless. So it's sized around the heat load.
Just to follow up on that question, what's the current situation with regard to connections to the grid for domestic persons? So, is there a market for the surplus electricity that you generate, or is that just goes free to the grid?
At the moment, there is no market. It's free to the grid in Ireland. There is a market in the UK for it. That's the problem with the Irish market. It's just not. It doesn't pay unless you're getting paid for all the electricity you generate.
Okay. And the connection process, is that difficult?
No, the connection process is very straightforward. It's an inform and fit. So basically, there's a form available on the ESB Networks website. You can download that, fill it out. Now, the type of grid connection equipment that you install needs to be type approved by the ESB, and once it is, you just send in the form with the actual specific details of the grid connection, and that's it. You can install your domestic generator. So,
but you're throwing away your surplus electricity.
Exactly. So there's no point in doing it, and it's the same connection process for PV, which is there's a bit more PV in the country than domestic CHP. So.
Sorry, just to follow up that, the ESB analysis or building grid in smart meters, will that change that situation?
Well, not really. No, like you need to have it's a commercial decision to pay for export is what's needed, really. Like the technology itself to record whether you're exporting or not is very straightforward. It's already there. Yeah, it's not the roadblock to the technology taking off. It's the idea of getting paid for export is the real driver, and that is a problem for PV systems as well, even though people don't really talk about it.
Kevin, just in relation to the heat load, the project you've worked on, could you just talk a bit about the challenges around that, finding the heat load and variability of heat load?
Well, what we've done is we've looked at the base load of heat in an older house. It's not going to, if you've got a new, like it's back to the point, if you don't have a heat load, you don't have a CHP project. And if you're talking about newer houses that are very well insulated with mechanical ventilation, heat recovery units, and there's very low heat load there. The system that we've designed is just too big for that, and it's not a market that we're looking at. What we're really looking at is older houses with bigger heat loads that are very difficult to retrofit. So the idea of a deep retrofit, which would cost you 100 or 150,000 for a bigger older house, may not appeal to as many people who spend 6,000 on a domestic CHP system and start, reduce their emissions by 20%. So it's a trade-off between the size of the heat load. That's what it is.
So then for industrial CHP, the challenges about heat load there?
If you're talking about the kind of processes that we work on, they're very heavy heat loads. They've been in existence for decades, and there isn't. Once you have that data about the operation of the plant that you're looking at, if a site has steam metering, that's great. If a site doesn't have steam metering, you can look at gas bills and that sort of stuff, and boiler efficiencies and run hours, and there's ways of analysing the heat loads that aren't that are very doable. It's not particularly challenging. I suppose that's the answer to that question. The industrial heat loads are very easy to quantify, and variability if say it's a seasonal heat load, that becomes more challenging. So like in a district heating system, that is a challenging CHP application. Now, you'll get good efficiency in the winter time, and in the summertime, the system losses will be very high from a district heating scheme relative to the demand. So that's a challenge, all right. But they're not the particular types of projects that we're involved in. So,
Thanks very much.
Hi, thanks for your presentation. I just have two quick questions. The first one is, I'm curious as to what, for the domestic CHP, what's the current achievement you've got for noise?
it's around 60 decibels. Yeah, so it's still a little bit louder. The target is 46. That's what we want to get to. But currently it's at 60. And the house that we're beginning the domestic trials in, the boiler room is separate to the house. So 60 decibels is actually quieter than a previous boiler that was in that room, believe it or not. So, yeah.
Thanks. Just the second question then really is that battery technology is coming on leaps and bounds. And if, for example, if I was considering a few years down the line to get a set of PV cells which are also increasing efficiency and to hook it up to a large battery in the house, is CHP at the domestic level going to be under pressure from that, given that CHP is still burning fuel at the house's location, shall we say?
There's no, well, I suppose the short answer would be no to that, because, okay, PV is getting better all the time and batteries are coming down in price, but they're still quite expensive. But there's no doubt battery prices are going to come down further. They're going to follow the same kind of path that solar did follow over the last 8 years. But the thing about solar is you're going to charge those batteries in the summertime. You're not going to keep them till the winter time. You know, you're going to use them. You might charge them during the day, but not to the extent that you would. Well, there's two things about it really. One, the whole thing is not based around electricity; it's based around heat. So you still have a heat load that you need to meet. And if you have say, if you're thinking about solar PV and heat pump technology, and using a battery to balance that, you're talking about a heat load, a very low heat load, a very well insulated house. That wouldn't be the target market for domestic CHP anyway. But we have been looking at batteries. I mean, batteries is something that's very interesting, but the cost of batteries are still quite high as well. So even at any scale, you're talking about spending the same amount on the batteries as you do on your PV system. Now there's a grant as well for them, but okay, it's just a different time of day.
Anybody else?
I suppose two questions around the nature of operation, whether it's intermittent or constant long term, and then whether or not the savings that you estimated up there reflect the intermittent operation. So first off, does CHP lend itself to relatively intermittent operation, otherwise peak demand or addressing things like that, like your graph showed up there a while ago? So can we turn it on for a couple of hours a day and it works well for that? I assume that in the domestic situation, because you have a low heat load in the house, you can quickly raise the temperature to something you need. And then the second part of my question is the 22% energy savings. Is that what's the 22% of over the year? So is it my annual spend on heating and electricity that I'm going to save 22% on?
Well, say.
That's two questions, sorry.
Yeah. The 22% is the primary energy savings. So that's what would have been burned in a power station somewhere else to supply the electricity that you generated, accounting for what you've done with heat as well. So that's what that 22% refers to. So it's the country as a whole, their emissions drops as a result of that. Now, does it lend itself to being switched on and off? It does to a certain extent, but it's not like a gas boiler, which will be cycling on and off a lot. it's like it'll come on and it'll run for 2 hours, and peak demand will still be met by a separate gas burner. So like 5.5 kilowatts wouldn't heat a very large house, but it would maintain the base load to it, and the peak load would be met by a separate gas burner. So that's you don't want to be stopping and starting it more than maybe 6 times, you know, on off, that kind of thing. The idea is to get the run hours up on it. You need to get the run hours to get the generation up to what would make it pay. I mean, if you're not getting run hours, the system isn't getting you the money that you need to get to make the payment back on the capital cost of it in the first place.
How do you envisage managing the 1 hours, otherwise switching in and switching out?
Yeah, what we're looking at there is basically, if you think about your house in the morning, all the water in the heating system is cold. Tomorrow morning at 6:30 you switch on. You will bring that up to, you'll have a gas burner and the CHP firing, and then say you get up to 50 degrees with both of them firing, so you get a rapid ramp up to there, and then you let the CHP take over there, and it'll gradually rise from that. Now the specific temperatures is something that's going to come out of the household trial, where we're cutting them in and out. And the idea would be that you'd be running at such a level that the CHP would stay on for 2 hours in the morning, and then shut off again, and then the same in the evening. So there's a little bit of, well, that's another thing that'll come out of the domestic trial. But the idea is that you still got peak capacity in the burner as opposed to the engine. It doesn't, the concept of modulating the CHP up and down doesn't work that well, because you'll end up putting in a 5 kilowatt CHP or bigger, and that you're exporting huge amounts then.
Okay.
So
That's good.
Just a question in terms of the national grid, it's decarbonising, you know, year on year, so another 5 or 6 years you could be at a point where just electricity says better carbon profile than using natural gas or oil. So how, in terms of using fossil fuels, CHP, do you think that's a threat to it, and that carbon emissions are likely to reduce significantly going forward?
yeah, well, that is, I mean, if you look at what's happened in the UK, they've got their grid is decarbonised very significantly since I started working on this project. Like the average emissions down there now are below 300 grams a kilowatt hour, which is very low. And I think there's two things that you have to think about when you're talking about it. The domestic CHP doesn't offset the average carbon. It offsets the peak carbon. So when the least efficient generators, the peaking plants, are being brought on. And the other thing about it is that, so we are going to transition to eventually electricity will be carbon free at some point, but the curve to develop to that point is very far out in the future. And part of that, part of the solution will be flexible gas generation, be the gas coming from bio anaerobic digestion is the most likely thing. So whatever, I would see renewable gas maintaining its place in the generation mix to back up intermittent renewables, because storage will always be a problem. Unless the cost of batteries falls hugely, and then you have pumped hydro, but I mean, the cost of pumped hydro is very high as well. So yeah, it's not something to be not. There's a transition, which is 30 years maybe, to where you have very low carbon electricity, and there's definitely a place for domestic CHP systems that have a life of 15 years in that 30-year window to decarbonise.
guess we can only say that that's been very interesting and not at all the usual run of talks that we have here. And I just like to take this opportunity to thank Kevin for volunteering on this something competitive data possibly even, but it's a brilliant opportunity for us to get an exposure to this process. So I'd like you to put your hands together in the usual way. And don't forget, next week, if you want to marry concrete and peat in wind farm construction, then you should be here. The week after that, it's modular and panelised building methods. Later that week, it's the annual dinner, so there's no shortage of events going in. Thank you for attending tonight.